Greetings, grade 10s. Welcome to the session. All right. Today, what we're going to go through in our mechanics journey is the subject of equations of motion. Once we've learned this little topic, we can actually really look at some exam questions and really put or piece the different questions together and how what we've learned is going to come together like a nicely well constructed puzzle. Okay, so there are only 4 equations of motion, but these equations stick with us all the way through till grade 12. Okay, in grade 12, the only difference with these equations, all right, is that we no longer in grade 12 deal with horizontal motion. Not that we no longer deal with it, but in this topic itself, though, we don't deal with it or look at motion in a horizontal direction, really, when it comes to the equations of motion. What we look at is we look at the vertical motion, so that delta x changes to delta y. So, like I said, delta x changes to delta y, but the equation of motion pretty much stays the same besides that fact. Okay. So there are 4 equations of motion. The reason why there are 4 is because we try to calculate, they all involve 4 variables. Okay, so if we have 3, of course, if we know 3, we can obviously calculate the 4th one. Okay, the first equation of motion I'm going to go through is Vf is equal to Vi plus A delta t, which is A times delta t. Let's just list the variables quickly. So, Vf will stand for final velocity. Vi, obviously, the I stands for initial. Initial velocity. The letter A stands for acceleration. And delta t stands for time in seconds. Always time in seconds. Okay. The second equation of motion that does exist, delta x is going to equal Vi times delta t plus half of acceleration times delta t all squared. Okay. Another variable that we see there, delta x, which we should be familiar with, is known as either the position or displacement. And we know that's measured in meters. Okay. Next one. Number 3. Vf squared is equal to, this is a very popular one, by the way, Vi squared plus 2A delta x. Okay, and then the 4th one that we get is delta x. I've hardly seen this one used as many as the top 3 though, but it does get used. Vi plus Vf divided by 2, and we usually bracket this, times delta t. Okay. So those are the 4 equations of motions, of course, and they all involve at least 4 variables. Okay, there are 5, of course, but we can obviously see the first one doesn't involve delta x. Okay, this is mostly just calculating either velocity, acceleration, or time. All right, so those are the 4 that does exist. Okay, so let's say, just to explain this with a word example, okay? Let's say you are in a car and you're on your way to school. Now, we can all picture this, right? So in a car and you're on your way to school and you're approaching a traffic light, or as we like to call them, the robots. Okay? You know that the speed of the car is perhaps around about 18 meters per second. Okay? Obviously, the car speedometer gives the speed in kilometers per hour, but because you're a good physics student, you've worked out already what that speed is in meters per second. So let's say if you're in a traffic light zone, not on the freeway, the speed now used to be 60. In some areas it's still 60, but it's around about 70 kilometers per hour. So, you know, you want to convert that to meters per second. That's around about 19.4 meters per second. So let's just check. 60 kilometers per hour is around about 16.6 meters per second. So this is probably closer to about 65. Okay, so if your car is traveling at 65 kilometers per hour, that's roughly around 18 meters per second. And that the car can also accelerate at minus 8 meters per second squared during braking. Okay, so that's just a general word scenario quickly, and you are given the acceleration and you are given the speed. Okay, now they'll ask you questions such as calculate the distance the car would cover during stopping. So in just what I read, or just the scenario I made up, we can see we were given a velocity, and it's a final velocity. Oh, sorry, it's the initial velocity, because if you approach a traffic light and it's a red robot, you're going to stop. So your final velocity will obviously be 0. Okay, so in fact, to make things a little bit more bad bougie, okay, if you got VI, which is your initial velocity that you were traveling at whilst you were approaching the traffic light, your acceleration was given at minus 8 meters per second squared. Why? Because that's what happens when you brake. You accelerate in the opposite direction, or you decelerate. And now they want to know the stopping distance. So that will be obviously your delta x. So we come here, we check, okay, what was the delta x formula that had acceleration in it. So what you could use, of course, is equation number 3, okay, which is VF squared equal to VI squared plus 2a delta x. Okay, because we're looking for delta x. Okay, there we go, found it, because we have VI acceleration and we know VF as well. So VF would obviously be 0 squared. Why is that the case? Because if you approach the traffic light, a red one especially, you're going to stop. Okay, so we need to think in sometimes literal terms here, mates. Okay, when we're approaching a red traffic light, we're going to come to a stop. All right, we must obviously know that. So we know VF, our final velocity is 0. Our initial velocity was 18 plus 2 times negative 8 delta x. That's going to equal, obviously, 0 squared is 0. And 18 squared, sorry, we've got to square that. 18 squared, let me get my calculator out quickly. 18 squared is 324. Okay. Plus, actually, the plus is going to change. Minus 16 delta x. Now, of course, we're going to take this entire bad boy over to the left-hand side to get 16 delta x. It's going to equal to 324. Divide both sides by 16. Okay, it's just divided by 16 quickly. And we know that the stopping distance that we should get, delta x, is roughly equal to about 20.25 meters. Okay, if he decelerates at minus 8 meters per second squared. Okay, so therefore the distance covered was 20.25 meters while he was braking before he got to the light. So they like to ask that equation, if he decelerates or accelerates at a minus acceleration value, will he stop in time? Because they'll give you the distance from where he is, from where he starts braking to the traffic light. At that acceleration, will he stop in time? And you'd obviously be able to test that. But we'll go through those examples, so don't worry about it. Okay, cool. So that's the equation of motion. So I'm just going to find some little exercise that we can use just to have a look. And what we'll do is, as an exercise, we'll just take an exam question paper. And I'll go through one with you first. And then I'll leave you one to try. Give you one question perhaps at a time that will involve also the previous weeks that we have looked at as well. And that can take us all the way through until you are doing entire questions all by yourselves. Okay, so going to be quite interesting. So let's go have a look. So what I have here, grade 10, is the DBE November 2015 paper. Sorry about that. That's found on the education.gov.za website under NEC examinations and pass the exams. And this is the 2015 paper. On the website, there are 3 years worth of common papers, so all the way down to 2015 to 2018. Very valuable for paper 1 and 2, and memos are included on the site itself to obviously help you and assist you with your learning. Okay, so that's pretty awesome. So let's look at the question here. A van is traveling at a constant speed of 54 kilometers per hour in a 40 kilometer per hour zone. This is a nice question. A policeman starts his car from rest just as the van passes him. Okay? And the police car accelerates at 2 meters per second. And per unit. No, that's until. Sorry, my eyes are bad. The police car accelerates at 2 meters per second until it reaches a maximum velocity of 20 meters per second. The policeman then continues driving at this constant velocity. Define the term acceleration. Okay, so basically acceleration, rate of change of velocity. Done. Okay, because that's the change of velocity divided by the change in time will give you a object's acceleration. Okay. To convert 54 kilometers per hour to into meters per second. So that is, I'll show that calculation now. I'm just going to do it on my calculator so I get the answer. 15 divided by 54 rather, divided by 3.6. Okay, cool. So there's a couple ways to do this. So let's just date it. So 2015 DBE November, grade 10, paper 1. So the 3.2 of this paper, what you do is you just take 54 kilometers per hour and you multiply it by 1 divided by 3,600. Or 1 divided by 3,6. Okay, it's basically like taking basically 54 divided by 3,6, right? And that'll give you your answer of 15 meters per second. And that's the conversion. I think I did show the conversion in class previously, or remember kilometers per hour, 1,000 kilometers in 1 meter, so which is basically 54 times 1,000 to get 54,000 meters, divided by 60 times 60, all right, to get time in seconds, 60 minutes in a hour, so times 60 to get it into seconds, which is 3,600, okay, and that'll also give you the same answer of 15 meters per second, okay, but that's the conversion. All right, let's have a look at the question 3.3. 3.3 says now calculate the time taken or the time it takes the police car to reach its maximum velocity. Okay, so now this is now an equation of motion question. For 3.3, now what do we know about it? We do know that the policeman starts his car from rest. So initially he's 0 meters per second. Whenever you see words like from rest or at rest, then you know it is starting from 0. VF is equal to 20 meters per second because he reaches 20 meters per second and then he travels at that constantly, and he accelerates at 2 meters per second squared. Okay, what is the time it takes for him to reach this velocity? Now notice what I'm doing here, girls. I am obviously writing down my information on the right hand side because I'm going to work on the left. This is highly valuable as it really helps you decide, or really helps you see what you have and what you don't have, and really outlines your question for you. It just outlines it nicely with what you've been given. I do know of some instances where people haven't worked out their answer correctly, but they have had their information correctly outlined. Once they have done that, of course, they can get marks. Maybe the marker might say, okay, let's give the person some marks by checking. Okay, he's outlined his information. That's fine. We can give him a mark for this. Okay, so it can help in your marking aspect as well. Okay, so don't take it for granted. Trust me, I've seen it happen. So now, based on our information, we go have a look at our equations of motion and we decide. So I think equation number 3 is going to be sorry, not number 3, number 1, because that's got delta t in it, because that's the variable we're looking for. So we always decide our equation of motion by determining the variable we're looking for. Okay, so it's got delta t in it, so we can either have used equation 1, equation I think 2, or equation 4. But in equation 2, that's going to give us a quadratic equation, and we know what that is. It can be extremely difficult, and we don't want to put ourselves through that. So what do? We just use equation 1. Vf is equal to Vi plus A delta t, because that's got everything we need, that we have, and it's got the variable we need to look at. So Vf is 20, Vi is 0, plus acceleration 2 times delta t. Okay, so we end up with just 0 plus that, so that's just 2 delta t. Divide both sides by 2. All right, therefore delta t will equal to 10 seconds. 3.4 now says calculate which vehicle, the van or the police car, is ahead at the time calculated in question 3.3. So is the van ahead of the police car, or is the police car ahead at 10 seconds? Okay, so let's just come back here. I need to add more layers eventually. But 3.4. Okay, so how do we approach this question? Well, we need to have a look at what is at 10 seconds, how much or what is the distance covered by either car. Okay, so the first one, we're going to have a look at the police car. So for the police car, we're looking for delta x. So I'm going to use the equation that says now, because I have time now, Vi delta t plus half A delta t all squared. I'm going to pop that in here and say, well, 0 is my Vi, my delta t, it was 10, but 0 multiplied by 10 or by anything is going to give you 0 anyway, plus half of obviously 2 times 10 all squared. Okay, so what am I going to get here? This is going to be 0 plus this, so I'm just going to work with this quickly because I'm going to save some space. So therefore delta x, in this case, half of 2 is 1. 1 times 10 squared is 100, so delta x is equal to 100 meters. Okay, let's choose another color for the van. Okay, now for the van, let's have a look at the information for the van. The van said the van is traveling at a constant speed. So if there's a constant speed, there is no acceleration. So in other words, the van, if I had to use the same equation, delta x is equal to Vi delta t plus half A delta t all squared. If he's at a constant speed, there's no acceleration. So 0 delta t all squared. Alright, which is basically going to give me 0 anyway. So my delta x is only going to equal to Vi delta t in this equation, because there's constant speed, so therefore there is no acceleration. Okay, so the speed he was traveling at was 15 times, and 10 seconds was for both. So I'm going to come up here, therefore delta x is equal to 150 meters. So at 10 seconds, who is ahead? We can conclude that the van is ahead. Okay. 3.5 now says how far along, or how far the police car, calculate, has to travel before it catches up to the van. Okay, So this is going to basically invoke a simultaneous equation. Okay, this is basically going to have to invoke a simultaneous equation. Both the van and the police car, they are at the same position when they catch up. So in other words, the position of the police car must equal the position of the van. Okay, so we just need to find out what's the common delta x, or common position. Okay, is that the position of the police car, which I'm going to call xp, must equal the position of the van, xv. Okay, so the position of the police car, which is this is because they must be at the same position, minus the 100 meters that it started at, must equal to the final velocity times the time. Okay? And basically what that is I get an equation that the position of the police car minus 100 is going to equal 20, which was the final velocity of the police car, times delta t. And this is my first equation. For the van xv, xv now minus 150, because that's where they were after 10 seconds, is going to equal to its final or constant velocity, which was 15 times delta t. Okay, and basically delta t was equal to 10 seconds. Okay, delta t was equal to 10 seconds. Okay, so therefore, if I need to find out the value of the police car, okay, the value of the police car xp should be equal to positive 100, because this just gets carried over. So positive 100 plus 20 plus 20 times 10. Okay. So that's now 100 plus 20 times 10 is 200, so that gives me 300 meters. So, and obviously I can plug that in here as well to find out the position. Okay, but basically when they catch up, they'll be at the same position. So to conclude, and I'm going to conclude here, the police car, all right, will only catch up, or catches up, to the van after 300 meters. Okay, after 300 meters. Oh, sorry, not ms. 300 meters. So that's probably going to take another 10 seconds. So that's probably going to be after 20 seconds. So after 20 seconds. Okay, after 300 meters, after 20 seconds. Okay. 3.6 now says write down the total time taken for the police to catch up to the van, which is basically going to be 10 plus 10, so it's going to be 20 seconds. Okay, 1 mark. Right, that one's done and dusted. Okay, in this question paper, this is a graph question, and I don't believe I've taken you through a graph question before. So let's just go through question 4 quickly. It's your graph question here in this question paper. This question paper, they give you a velocity versus time graph for a racing car that's moving eastwards, and of course they've included the compass directions for you to see which way is east. Okay, so we've got different positions A, B, C, D, as well as E, and different points on the graph. Velocity obviously being measured here on the y-axis and time on the x-axis. The first question says or asks us to write down the initial velocity of the car. Initial velocity now from the graph, where is it starting from? Somebody, either Mia, Nabila, or even Jordan, because I'm sure you can read a graph. What would be the initial velocity of this racing car from the graph? Anybody? Come on. Just read it. It's just reading it off the graph.
I said, wouldn't it be like 30?
Okay, 30 is the correct value. Yes, excellent. Thank you. Okay, so finish that answer off for me in velocity terms, please, Mia.
Meters per second.
Thank you kindly. Okay, so our answer is literally written just like this, 30 meters per second, and that's, we're done. And that's obviously position A, or point A on the graph. Okay, all we did, read it straight off the graph. Okay, now another question that we can also read straight off the graph with absolutely no calculation whatsoever is 4.2. Write down the speed of the car at time t equals 10 seconds. Now, time 10 seconds is not labeled here. So 10 is somewhere in between here somewhere, okay? So now what we need to do is look at the position or look at how the graph looks. You can see the gradient, because it's a flat line, the gradient is equal to 0. If gradient is equal to 0, nothing's changing. This is a parallel line with the x-axis. So, at 10 seconds, what would be let's say 10 is in the middle of 5 and 20, for example, somewhere around here. What is the speed? We could just read that off the graph. The speed stays the same from 5 seconds to 20 seconds. So, what is the graph at time equals 10 seconds? At the 10-second mark, what is the speed of the racing car? Extremely straightforward. Come on, girls.
Isn't it 40
Do you mind finishing that answer off in...
meters per second?
Yes! Yeah! I feel like that's a light at the end of the tunnel. Fantastic. Excellent. Okay. So, 4.2, it is 40 meters per second. Now, before we progress, I just want to find out, does everybody understand why it is 40 meters per second? Okay. 4.3 is a little different. 4.3 says, describe the motion of the car for the section labeled CD. First of all, at position D is 25 seconds, and at position C is 20 seconds. So for 5 seconds, basically this is the change in position from C and D. But we also know that there's a change in velocity that's coming down from 40 meters per second to 0. Because on this line here is 0 meters per second, because that's the 0 mark here. So from 40 meters per second down to 0. So something is obviously taken place. And the question is phrased in such a way that we need to describe the motion. Okay? So we could say the speed decreases from 40 meters to 0, or we could say that the car clearly slows down, okay, and finally comes to a stop. The car slows down and the car finally comes to a stop. Okay, we can see that in the graph because all the way down here, from C all the way down this line here, the graph is decreasing, 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 or the speed, velocity rather, is decreasing, 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 even past the initial speed of 30 meters per second is decreasing, and when it comes here, it stops. Okay, we're not worried about the D to E motion just yet. I don't think there's a question here. Okay, 4.5, yes, but we're not worried about that motion just yet. Okay, so that was 4.3. 2 marks. Now 4.4, support your answer in 4.3 by calculating the acceleration for section C to D. So, acceleration in calculating or calculate acceleration from a velocity time graph is taken by the gradient. Okay? So acceleration is basically equal to the gradient of the graph, which is equal to the change in y over the change in x. Okay? Which is basically equal to y2 minus y1 over x2 minus x1, which is the points on the graph. If we remember straight line graphs from grade 9 or even in grade 10, if we've done parabola graphs or hyperbola graphs, this gradient equation doesn't go away. Okay? So I'm going to choose obviously 40 and 0. So I'm going to choose y2 as 0 minus 40, and my x position is going to be the final position also, so 25 minus 20. Okay, where do I get those points? So over here, my y position, y1 is 40 and 20, and my y position number 2 is obviously 0, and my x position is also 0. Or my x position rather is 25 is my x2 position, so that's 25 and 0, and my x1 position is 20, and my y1 position is 40. So I end up with this equation. So this is y2 was 0 and x2 was 25. These coordinates obviously go together. Okay, they are classed as 1, and then of course 40 and 20, they are classed as 1 point as well, because a point on a graph always has an x and a y point. Basically, after that, we're going to end up with minus 40 divided by 5, and that's going to give us an acceleration of minus 8 meters per second, meaning the racing car is slowing down, so he's hit the brakes. So he's accelerating in the opposite direction, which is now no longer east, but he is accelerating in the direction of the westerly direction. Okay, got that? So it's a negative acceleration. Okay, we've supported our answer there, and that's for 4 marks. Okay, 4.5, without any calculation, compare the magnitude of the acceleration of the car in part DE with that of part CD of the journey. Write down only greater than, less than, or equal to, and give a reason for your answer. Okay, well, my answer without any calculation for 4.5, ladies, I'm just going to let you look at the graph quickly. Can we see that from position C even to E? My question that I would like to ask, it's not rhetorical, I will require an answer, is if you look at the straight line that runs all the way from C down to D, and then from all the way down to E. So let's take that entire line of C to E. My question to you ladies is the following. Do you think that the gradient between C and D is the same gradient as that of D and E? Yes or no? First answer that comes to your head. Tell me. Or does that line change in any way? Or does it look like a complete straight line from C down to E? Does it change or does it not change?
Doesn't look like it changes.
Okay, excellent. That's Mia's observation. Jordan, what is your observation? Does the line change in any way, or does it look the same all the way down from C to E?
It looks the same.
Excellent.
Besides the fact that it's getting negatives.
Awesome, but it's the same line, eh? The line doesn't look like it changes into a straight line or looks a bit steeper or flatter. Looks like one straight line. Awesome. Thanks, Jordan. Nabila, what say you?
I don't think it changes.
Okay, excellent. Guess what? All 3 of you are correct. Okay, the line doesn't change. So if the line doesn't change and there's no clear observation, all right, to support that the line does change. So there's no clear observation that the line changes. It's just a straight line. My next question is, will the gradient change? Or will the gradient be different between points C and D and E, or the gradient be the same? If the line hasn't changed, what say you, Miss Wheatley?
Oh, goodness.
Remember, guys, let me maybe just put this into perspective. Remember, girls, that the gradient is only the difference between 2 points on a graph. Okay? So if we take the points between D and E, because we've taken the points for C and D, so if we now take the points D and E, remember we're not using a calculation here, but basically C and from position C to E is almost like a graph on its own. So imagine that was just one straight line, and you took the difference, or you took the gradient between the points C and D. All right, and now you want to take the points between D and E, but the line hasn't changed. So surely, by intuition, any 2 points on one straight line graph should give you the same gradient. At least that's what the rules of a straight line graph is in mathematics. Am I correct or am I correct?
I think you're correct.
Which one or two? The first correct or the second one? I really don't know.
Both, I guess.
Fantastic. Okay, so what say you now? Is the gradient going to be the same from between C and D and E?
If it's like straight and it's not like changing anyway in any way, then I think so.
Excellent. Thank you very much for your answer, Mia. What say you, Jordan? Just based on my little explanation. What say you, Jordan? Do you think it's going to be the same?
Yeah, I think so.
Cool. Remember, you're just telling me what you think, eh? Cool. What about you, Nabila? What do you think, Nabila? What do you
Yes.
think? Oh, you think yes too. Guess what, ladies? I like the way you
I
all
think it's going
think.
to stay the same.
Well, I like the way you all think, ladies. You all think basically with the same mind almost. All right? An intelligent one. That is yes. It is going to be from the options that they've given us there equal to. Okay? In other words, the gradient from C or the ask what they ask. The magnitude of the acceleration from C to D is the same from D to E. So we're going to write down obviously our answer as equal to. And the reason is because the gradient is the same gradient. Okay? Spectacular. Beautiful. You know, if I was French. You know? Spectacular. Excellent. Now, 4.6, this is your big daddy question. Okay, determine the displacement for the motion of the car. Now, last week, remember, how do we now determine the displacement from a velocity time graph? It seems absolutely absurd. No, it does not. Okay, we take the area underneath the graph. Okay, so what we're going to do is we're going to have a look at this graph. Okay. So we can see we have a trapezium. Okay, we have a trapezium-like looking shape. Okay, so let's see. I forgot the area. Plus, okay, we got an area of a trapezium plus the area of a rectangle, plus the you see, yeah. Plus the area of a triangle over there, and then because that other triangle forms into the negative zone, is going to be minus that of a triangle. Okay, cool. So this is how it's going to look. Okay, if this started down at the bottom, then there would have been a straight trapezium, but we've got a trapezium or half a trapezium here. If we turn this on its side, we've got half a trapezium. Okay. Plus this little triangle over here as well. So we've got half a trapezium. But this little triangle here, this is not part of this. So we're looking at just A to B. Okay, and this is sectioned off there. So a little bit of A to B there. Then we've got B to C, which is a rectangle. And then we've got this little triangle here. And then, of course, we've got this other little triangle at the bottom. But that's going to be minus. So let me show you how it's going to be done. We got an area of a trapezium, or let me just start out by doing this. Displacement or delta x, whichever one you want to write it as, is equal to the area under VT graph, velocity time graph. Okay, which is delta x now is equal to your area of a trapezium, okay, in brackets, plus your area of a rectangle, plus your area of a triangle, minus the area of another triangle. So we end up with half of 40 plus 30 times 5, which is the area of a trapezium, plus the rectangle over here. 20 minus 5 is 15, and obviously 0 to 40 is 40, so we end up with 15 times 40, which is length times breadth, plus half of base times height. So half of the base here from 20 to 25 is 5, so we have plus half of 5. You just bracket this also and square this. Half of 5 times height, which is also 40, and bracket that as well. And now we got minus little triangle at the bottom here. You can see from 25 to 27 and a half there, that's 2.5 seconds, so that's base, so that is half of 2.5 times the height at the bottom there, because it's a negative graph. That line coming straight down is 20, so it's minus, so we don't have to put in minus 20 because we got that this all in here. Okay, it's minus, or we could have said plus and then put the minus 20 there if we wish, but it ends up being this anyway. So we're going to press equal, or not press equal, but write equal, and then we're just going to, oopsie, sorry about that, my mouse hovered over my file explorer there. So we should end up with, let's take half of 40. Okay, let me just put that into my calculator quickly. You're welcome to do this yourself. Half times 40 plus 30, which is 70, so half of 70, times 5, brackets, plus 15 times 40, plus half of 5 times 40, half of, sorry, 5 times 40, yeah, 40, yeah. And minus brackets, half times 2.5 times by 20. We get an answer of 800, and therefore delta x equal to 850 meters. Alright, so I'm going to give this question to the class to attempt on their own. Question 3 of 2016, DBE November. And it's a very small question, not that big, but okay, it's about 17 marks. But basically, I'm sure you can all read, but let's just read it quickly. A taxi is traveling at a speed of 25 meters per second when a traffic light 40 meters ahead changes to red. Define the term acceleration. I'm going to let you skip acceleration definitions for now because I'm sure you guys all know what it is. Let's focus on 3.2 onwards. The driver takes 1 second to react. In other words, that's his reaction time before he slams the brakes. The taxi then stops within 2 seconds. Okay. 3.2 is the velocity and acceleration of the braking taxi in the same direction as it moves towards the tracking light. That's just a yes or no answer. Give a reason for 3.2 and 3.3. And 3.4 is now calculate the distance the taxi driver travels during the reaction time. And the reaction time was 1 second. So we need to calculate the distance that the taxi traveled. And then 3.5 is, will he stop at the traffic light? Show all calculations. Okay, cool. So this is an equation of motions question. Okay, and I'm going to give until the end of the session for this. Okay, so we might only mark it next week. Okay, but let's give it until the end of the session to attempt all of these questions from 3.2 down to 3.5. I'll check in at about 25 past maybe, just for question 3.5. See if we're not there yet, we'll mark it next week. Okay, let's go, ladies, let's go. And that does conclude my time with the grade 10 class. We will mark the question paper that we see here. We will mark the question paper next week in the following session. Thank you so much for joining me this week, and we will mark this question paper next week, as well as continue with learning energy, which is the last topic in mechanics, and then we will practice some more question papers, and then we'll put this section to bed.